Hello everyone. Today we are going to analyze this cantilever beam. In this beam, there is uniformly distributed load from the point C up to the free end B. The load starts from a distance of A from the fixed end. The span of the beam is given as L. Using this rule, we can find RA. RA is acting upwards, so it will be positive. The UDL is acting downwards, so it will be negative. With the UDL, we have to multiply the distance. This distance is L minus A. For RA, we will get W into L minus A. Now, from the point B, I am going to take moment about A and find the moment MA. In this case, I have to follow left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. The load W is acting in the clockwise direction, so it will be negative. We know that for the uniformly distributed load, we have to multiply the area with the distance of center of gravity. We know that the uniformly distributed loads shape is a rectangle. Here we have W and here we have W. The length is L minus A. When we multiply W with L minus A, we will get the area. We know that the center of gravity for a rectangle lies in the center. From the center to here, the distance is L minus A upon 2, but we are finding the distance up to the point A. So we have to add the rest of the distance, which is A. The moment MA is acting in the anti-clockwise direction, so it will be positive. For these two terms, we can take LCM. We have to multiply A with 2. Minus A plus 2A, it will be plus A. We know the formula for A square minus B square, A plus B into A minus B. Using the formula, we can write these two terms as L square minus A square. For MA, we will get W upon 2 into L square minus A square. Now, from the point A and towards the point B, I am going to find the shear force values. The shear force at just left of A will be 0. The shear force at just right of A will be W into L minus A. The shear force at C also will be W into L minus A, because up to the point C, we have only this vertical reaction. Let us find the shear force at B. In addition to this, we have the uniformly distributed load. It is acting downwards, so it will be negative. We know that with the UDL, we have to multiply the distance. The distance is L minus A. For the shear force at B, we will get 0. Here you can see the shear force diagram. Now let us find the bending moments. To find the bending moment in the point A, we can use the right-hand side rule. In the point A, we have MA. It is acting in the anti-clockwise direction, so it will be negative. To find the moment at C, we can use the left-hand side rule. The UDL is acting in the clockwise direction, so it will be negative. We know that for the UDL, we have to multiply the area with the centroid distance. The area we know, W into L minus A. We know that for a rectangle, the centroid lies in the center. The centroid distance to the point C is L minus A by 2. For the moment at C, we will get W by 2 into L minus A the whole square. The moment in the free end B will be 0. Here you can see the bending moment diagram. Under the UDL, the diagram should be in the shape of a parabola. Now, using the MACAULAY'S method, I am going to find the slope and deflection in the points C and B. We have to make sections. In this beam, there are two different parts, AC and CB. So we have to make two sections, one in AC and one in CB. I have made both of the sections at a distance of x from the point A. Now I'm going to find the moment about the sections from the point A. In this case, I have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. MA is acting in the anti-clockwise direction, so it will be negative. RA is acting in the clockwise direction, so it will be positive and the distance is x. The UDL is acting in the anti-clockwise direction, so it will be negative. For the UDL, we have to take this distance. This distance is x minus a. We know that with the UDL, we have to multiply the distance and then the distance by 2. So w into x minus a the whole power square upon 2. This term should be separated by this line. Now we have to equate the movement to ei d square y upon dx square. We have to integrate on both of the sides. When we integrate this, we will get dy upon dx. We can integrate these two terms using this formula and this term using this formula. In this term, there is no x, so the integration will be x. When we integrate x, it will be x square upon 2. C1 is the constant. When we integrate x minus a the whole power square, it will be x minus a the whole power cube upon 3. 2 into 3, it will be 6. Again, one more time, we have to integrate on both of the sides. When we integrate this, we will get y. When we integrate x, it will be x square upon 2. When we integrate x square, it will be x cube upon 3. In this term, there is no x, so we have to multiply with the x. C2 is the new constant. When we integrate x minus a the whole power cube, it will be x minus a the whole power 4 upon 4. 2 into 3, it will be 6. 6 into 4, it will be 24. In the point A, there is a fixed support. In the fixed support, there will be no slope. So when x is 0, the slope will be 0. In this equation, for x and for dy upon dx, we can apply 0. When we do that, we should not consider this. In this way, for C1, we will get 0. Also, in the fixed support, there will be no deflection. In this equation for x and y, we have to apply 0. We should not consider this term. In this way for C2, we will get 0. Let us apply the values of C1 and C2 in these two equations so that we will get these two equations. First, let us take the slope equation. To find the slope when x is less than a, we should not consider this term. We have to only take these two terms. We can take w upon 2 outside and we can take ei on the other side. We will get this equation. Let us keep this equation as number 1. To find the slope when x is greater than a, we have to consider this term also. From these three, we can take w upon 2 outside. For these terms, we have to take LCM. We have to multiply them with 3. Using this formula, we can expand this like this. Here there is negative sign, so we have to change the signs. Finally, we will get this expression. Let us keep this expression as number 2. Using these two equations, we can find the slope at any point of the beam. To find the slope in the point C, in any one of them, instead of x, we have to apply a. I have taken this equation. Instead of x, I have applied a. In this way, for theta c, I will get this expression. To find the slope in the free end B, in this equation, instead of x, we have to apply L. In this way, we will get this expression. Now let us take the deflection equation. When x is less than a, we should not consider this term. Only we have to take these two terms. After simplifying, we will get this equation. Let us keep this equation as number 3. When x is greater than a, we have to consider this term also. After simplifying, we will get this equation. Let us keep this as number 4. Using these two equations, we can find the deflection at any point of the beam. To find the deflection in the point C, in any one of these two equations, instead of x, we have to apply a. I have used this equation. Instead of x, I have applied a. Finally, we will get this expression. To find the slope in the point B, in this equation, instead of x, we have to apply L. Using this formula, we can expand this term like this. Finally, we will get this expression. Here I have summarized of what we have done. Now we are going to end this session. Thank you for watching this video.